12. 12 is pretty simple. It is multiple choice. I tried to give you some more multiple choice on this one so you can see what the multiple choice questions look like. All right, 12. Basically in 12 what you have is there's a ceiling, there is a block being pushed onto the ceiling. It's accelerating in this direction, and this is 12. And the push is coming from this direction. They're giving you, in the problem it's kind of hard to see, but this is the angle they're giving you, theta, right there. The question is, what is this? What is the friction force between the block and the ceiling? That's what we're trying to find. Okay, so this would be really easy if what? If it was flipped and the block was just on the surface, because we know on the surface, friction force is equal to Fg mu, or in other words, m, the mass of the block, times g, times the coefficient mu. So what's the difference here? Well, there's two things really that we need to look at. Okay. And yeah, so on our free body diagram, when we look at this block, okay, the frictional force, okay, between this and the block is still going to point this way, right? But remember that is coming from the normal force here, right? And since it's flipped upside down, you're going to lose some of the normal force to gravity. Okay, Fg, F friction. So your normal force here is smaller than it normally would be because gravity's pulling down on it. And then this would be your applied force from the push. Okay, so one of the things that we need to realize is that you're gonna. Why did you ever sit behind this? You're gonna I know. One of the things that you need to realize is that your frictional force is going to be Fg minus your frictional force, or frictional force minus Fg. Yeah. Okay. What's the other thing that comes into play here? Okay, so the friction force is caused by some force pushing the block into another thing, which is right here. Okay. Is this block being, or is this force being applied at a 90-degree angle? No, it's at some angle theta. Right, so we're gonna have to figure out what to do with that angle theta in order to get the portion of it, the component that's pushing into the block. In other words, that part right there. Which trig function will I use for that? Sorry? That's sine. Okay, opposite side. So what we could say here is that the force of friction is going to be equal to things. It was you. Who else was it? Was it though?
It wasn't me.
Okay. Force of friction. I basically fixed it. Okay. It's going to be equal to. What is it? Yeah. Okay. It's going to be equal to the normal force multiplied by mu. Okay. It's actually not the force of gravity in this case because the normal force. Like we said before, gravity is pulling some of that normal force away. So it's going to look like this. It would be, okay, F, what is it? Yeah. This force right here, sine theta. So the component that's going into the block, okay, minus whatever part is being taken away by gravity. Okay, that would be this force right here, whatever is pushing the block into the ceiling. Does everyone understand where I'm getting that from? Because I feel like I'm not explaining it very well. Yeah.
That force to up is greater than that.
Right, because that's what's pushing it into the ceiling. Okay. So our net force upwards is going to be equal to the force we push the block into the ceiling with, F sine theta, minus gravity pulling down. Okay, right? We got that. That force is what causes friction, so then you just stick a mu on the end. That's number 12. Number 13 is also multiple choice. So let's look at 13. Should be easy to knock this one Well, we talked about this in my class. So hopefully if you hadn't looked at 13 before and you're looking at it now, you can answer this question. 13 says you're sitting in a chair at your computer, right? And says the chair exerts an upward supporting force N on you, and gravity exerts a downward force Fg on you. To a fairly good approximation, N is equal to negative Fg. In other words, these two forces right here, okay, so this would be the normal force and the gravitational force, are of the same magnitude. That's why you don't sink into the floor or like fly away from Earth. Okay. The question asks, is this an example of Newton's third law? For people in my class, what's the answer? No. Why?
Because they're not the same force.
They're not the same type of force. Okay? A normal force is a contact force. It's electromagnetic. Okay? Electromagnetic. The force of gravity, we didn't really talk about this. This is a field force, meaning that it operates at distances. This is a field force, and it's gravitational. And what we learned in my class today is with Newton's third law. For Newton's third law, for those pairs to work, they have to be the same exact type of force. So this is not an example of Newton's third law. The explanation they give is it's due to the fact that your upward or downward acceleration just happens to be almost negligible. Right? So these two things are not equal because it's a Newton's third law pair. It's just because that's how it is. But I put that one on there for a reason, because I knew we were going to talk about that in class. I don't want to go back. Okay, and then 14, another multiple choice. 14 shouldn't have been hard. Yeah. 14, basically you have a person in an elevator, right? It says that the elevator is accelerating upwards, so our net force has to be pointing upwards. Okay? That means that this normal force has to be what compared to the gravitational force? It has to be bigger. Those are the only two forces in play in the y direction in an elevator. So your normal force has to be greater than Fg, otherwise you wouldn't have a net force pointing upwards. So this would be it. If it's not greater, then you don't move upwards. You don't accelerate upwards, sorry. That's 14. Alright, let's look at the last one, and then we can all go home. Oh yeah, there's two parts, right? Yeah.
Wait, this looks
Okay.
exactly like one of
15's not bad. This is like a very typical block on an incline problem. And basically what you're being given here is incline, some angle theta. I think that gives it to you. Gives you a block with the mass m. And then it also, here's the thing that I didn't notice at first. It does give you this height. Okay, it gives you a height, and then it also gives you what mu is equal to.
So you use friction.
Okay, so yeah, you know friction's involved in this problem somewhere. Okay, the problem is, what is the speed of the block at the bottom of the ramp? No, speed. What is the velocity at the bottom of the ramp? Okay, what force is going to cause this object to slide down the ramp? Gravity is going to cause the object to slide down the ramp. What force is going to be the one involved with this frictional force? Gravity again, okay? So with our ramp problems, we're always looking at the force of gravity. It's just the force of gravity is split into two ways. One makes it slide down, the other makes it core, right? And apply friction. So if we're looking at the free body diagram of this block, we've got one force here that's going to make it slide down the ramp. We've got another force here that's going to pull in the opposite direction. This is our frictional force. So really what we need to do is two things. One, we need to figure out how we can find both of those forces, and then two, figure out how they apply to our net force. Okay? So let's first look at the net force. Okay, F net is equal to ma. So in our free body diagram, there's only two forces we're really concerned with. How would we find the net force?
We're getting mass.
Oh, I know, but I'm just talking about this. Just use these two terms.
Oh, well.
Sorry? One minus the other, right? To find our net force, so you could say slide minus friction is equal to ma. what we want to do is go ahead and substitute in our variables, right, for this. So for the sliding force, we know sine slides. So we could say Fg sine theta for the sliding force minus Fg cosine theta. What else do I need to add? Mu, because it's a frictional force, equals Ma. And then the mass we get from the block. From here, it should be very easy for you to solve for A. Right? You just plug in and solve for A. I'm not gonna show you how to do that in the sake of time. If we know A, then what we can do is this. We can use this equation. Vf is equal to Vi plus At. Vi being what? What can you assume about Vi?
VI is
In this problem, is the block already moving when we look at it? It's 0. Vi is 0 is what I'm trying to get you to realize. So once you solve for the acceleration here, okay, we know we can plug it back into this equation. Hold on, I think this is the same mistake I made the first time. Well, it's not a mistake, but there's an easy way to do this. Yeah. Okay. Here's. I spoke too soon. Fg is the force of gravity, so it's mass times 9.8, right? M times A. I spoke too soon. That is one way to do it. I couldn't get it to work. Since we don't know what, why wouldn't that equation work, the one I just erased? Vf is equal to Vi plus 18. We don't know time. Well, we know Vi. Vi is 0. We're assuming it starts from rest. Like it's placed on the slope and then somebody like takes their hands away. Okay. We don't know time, so what we're going to use is, once we solve for A, yeah, we're going to use the time independent equation. 2A delta x. Okay, 2A delta x. Vi is 0, so we get this. Vf squared is equal to 2A delta x. We know A, we're trying to solve for Vf squared. We need to know what delta x is. This is where I got stuck. I didn't realize in the problem they give you, in mine, it gave me a height of 8.9 meters. It says it in your problem, it's just not on the picture. And then it also gives you an angle theta. Okay, so how can you find, this isn't really delta x. What distance from this triangle am I going to find? The hypotenuse. This is what I want to find, because that's the distance it's sliding down. Okay, so for this, this would be a sine function, opposite in the hypotenuse. Sine theta is equal to O over h. So h has to be O divided by sine theta. So you get the delta x. It's not really x, delta x, because it's at a slope, right? You get the delta x from there. And then you plug in with the a that you found to get your final velocity. Okay, that's not too bad. Okay, for the second part of this problem, it's really, well, I think it's easy to make a mistake on the second part of the problem, even though it seems really simple. Because there's one thing I forgot to consider when I did this. For the second part of the problem, basically what it's telling you is I'm going to flip the direction of my ramp. The block is now off the ramp. It slid off of it. And it's asking you how far is it going to travel before what? Before it stops. Okay. What's going to make it stop? Which force? Okay, good. We know friction is the force that's slowing it down, causing it to stop. Here's where I made a mistake. What I did is I used the force of friction from the first part of the problem. Why can't I do that in this problem? In this part. It's not on an angle, it's not on a slope anymore, it's on the ground. So I need to get rid of that sine theta component, or cosine theta component. So the force of friction here is going to be mg mu. Just very simply, there's no trig here because it's on a flat ground. So you'd have to resolve for the force of friction, right? If we're looking at our box now, free body diagram, there's only one force. It's moving in this direction, by the way. What one force is it? It's only friction, because we know since it's on level ground that normal and gravity are going to cancel out. There's only one force now, friction, slowing it down. So we can say that in F net equals ma, we can say that our net force is the friction force. Okay, so we can say mg mu is equal to ma. You can see that a lot of times your masses cancel out when you're dealing with friction, which is weird, but it does. And from here you can solve for the acceleration of your block. Okay. What I would do is make this acceleration negative. Why? Because it's slowing it down. It's going in the opposite direction of its motion. Right? So your acceleration here, make it some negative number. I'll put negative question mark for now. Okay, now that we have the acceleration, we're looking for delta x. What other piece of information do I know from the first part of the problem? Well, now it's initial velocity, right? Okay, I know this one. It was my final velocity in the first part, but now that it's off the ramp, it's going to be my initial velocity. Okay, so which equation would I use to solve for delta x? Okay, why can't I use VIT plus 1
Oh, we don't have time.
We don't have time. If you don't have time, it's probably good to try to use the time independent equation first. 2a delta x. Okay, I know initial velocity. What's final velocity? 0, because it's coming to a stop. Okay, I know a, I just solved for it, and then I could rearrange for delta x. That problem right there is like, I don't know, it's your very typical block on a ramp problem. Find out if the final velocity at the end of the ramp and then figure out how far it's going to slide. That sounds pretty good. Did you forget mu?
No, I did like kilograms times
Well, how many kilograms is your block? So you did 3.9 times some
Oh,
other decimal?
I didn't realize.
Yeah, there you go.
I got 0.5 years old.
All right.
So, -3.